All right, so I'm so excited because I really feel like this is the beginning of chemistry. Up until this point, it's been middle school review, it's even been a little bit of physics, but this is truly, truly chemistry. So, elements, ions, and atoms, oh my, elements, ions, and atoms, oh my. I can memorize names and symbols of selected elements. So let's get down to the micro level. Let's find out what are the building blocks of all matter. And of course, that's elements. That's elements. About how many naturally occurring elements are there? About 88. Look at that. I'm only going to ask you to memorize 43 of them. Only 43 of them. Okay? Out of the 88, the rest have been synthesized. The rest have been synthesized. There are 118. So 88 minus 118 is 30. So the rest are man-made. What is the most abundant element on the earth? Joey. Joey. Oxygen, yes. The most abundant compound, by the way, is sand, silicon dioxide. There is more SiO2 than any other compound. So my question for you is, what is the second most abundant element?
Nitrogen.
Okay, let's go through this again. The most abundant compound is silicon dioxide, sand, SiO2. Okay, so what is the second most abundant?
Oxygen.
The most abundant compound on Earth is silicon dioxide. What if oxygen is the most abundant element? What is the second most abundant element? What are the most abundant elements? The three most abundant elements that we are made up of? Oxygen, carbon, hydrogen. He is on fire now after being completely like frigid cold up until this point. This is the Earth. 49% of the Earth is oxygen. Silicon, 25.7%. Some of the things you guys said, nitrogen, 0.03. Epic fail. I think I heard carbon, 0.08. Epic fail. So it's mostly oxygen and silicon. For you guys, and me, I guess, I have to admit that I'm human too. Oxygen is 65%, carbon is 18%, hydrogen is 10%, and the rest are just teeny tiny amounts. So, what are the elements symbols made up of? They're made up of one or two letters. The first one is always capitalized. If you're one of these people that do not like to capitalize letters, then we're in trouble. If you're one of these people that like to capitalize every letter, we're still in trouble. Why do some element symbols not match their names? Because, as we've already talked about, they're ancient. We've known about them for a long time. Like gold. Gold, for the longest time in human history, was referred to as aurum. A-U-R-U-M, aurum. Okay, only in recent years do we refer to it as gold. Okay, so that is why some of the symbols do not match their English names, because they were around back in the Latin days. They were around back in the Latin days. Latin. For example, iron. I know there's a local company that likes to collect scrap metals. So they'll tell you that they collect ferrous or non-ferrous metals. All right, so here's some Latin names. You recognize some of them? Are there names here that you're familiar with? How about plumbum? That kind of reminds you of what? I was thinking more plumbers. You know why? Because at one time, indoor plumbing used lead pipes. Okay, yeah, but it took a long time. Like we're talking into the 1800s before we realized that lead plumbing was causing mental problems. For example, the first major city to have indoor plumbing was Rome back in the 4th century. Now keep in mind that Rome fell around the 5th century. Okay, so Rome was an incredible institution, an incredible empire. Probably should have lasted forever, but it fell. So historians talk all the time about what were the forces that brought Rome down. And you realize that some historians truly believe, and I think there's something to it, is that indoor plumbing caused the downfall of Rome. Why? Because if water becomes acidic, which is actually pretty easy for it to do, especially if any chemicals are added to it, it can dissolve the lead. Awesome. Lead now dissolved in water gets consumed by the people, and lead in the 1800s was proven to cause all sorts of neurological problems, including psychosis. You do realize that in the 5th century, Rome elected a donkey to be emperor. Okay? I mean, that tells you, yes, a donkey was it got really kind of nutty there at the end. All right? So, makes you think. Went nuts. Okay. The other one that should be familiar with you is the fact that my ancestors, the conquistadores, the Spaniards, when they landed in South America, they found a land that had Native Americans in it. So what did they do? They conquered them, because that's why they're called conquistadores. All right? Guess what they found that they had a lot of? Silver. Silverland. All right. So Argentina is basically Silverland. What if I was to give you some aurum? Would you like me to give you some aurum?
Yes.
Aurum? Good. Okay. Gold. What? Just remember, I've got that Quizlet for you. Okay. Don't forget that. Why do some elements have temporary names? Because they're still arguing over them. Okay. Number 3, Ayupak. Who is Ayupak? Ayupak is Tupac Shakur's little brother. Tupac, of course, he deceived his own death. No, what am I thinking? I think I've had too much lead. Yeah. No. Some people believe that he faked his own death, along with Elvis and John F. Kennedy. Ayupak, of course he's still alive. He's Tupac's little brother. And interesting enough, Ayupak, if you use his name as an acronym, spells out International Union of Pure and Applied Chemistry, which has nothing to do with naming these things. It's Tupac Shakur's little brother, Ayupak, who names them. And last year, he finally named an element after us. That element is Tennessee, which kind of irritates me because Oak Ridge is responsible for, I believe, 4 elements being discovered. Okay, not Tennessee, Oak Ridge. So why wasn't it called Oak Ridgium? I think it should have been called Oak Ridgium instead of Tennessee. Now, the Quizlet that I created for you is based on this chart. You don't like Quizlet. You hate Quizlet. then take out your cell phones and very quickly take a picture of this so that you have something to study. You have 15 seconds to get a picture of this if you don't want to use Quizlet. 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, what I'm going to do, first of all, I'm not going to quiz you on all 44, but I'm not going to tell you which one of the 44 I'm going to quiz you on. It's only going to be 20. It'll be a PowerPoint slide with, on one side, you'll see 1 through 10, and they will be chemical symbols. Guess what I'm going to ask you to do? Correctly spelled names. On the other side, I will give you 11 through 20, which will have chemical names, which I will expect you to give me the symbols for. Correctly spelled symbols.
You aren't shocked, you aren't awed, you might not even be paying attention anymore, but when atomic theory was first proposed, it sounded pretty crazy. And yes, we call it atomic theory, using the scientific definition of theory, which is a well-tested set of ideas that explains many disparate observations, not the colloquial definition of theory, which is a guess. Though luckily there's no one running around anymore saying, atoms are just a theory. But it wasn't that long ago that people were running around saying that, and you want to know who settled it for good? Einstein. Atoms had been postulated for a long time by the 20th century, but it wasn't until Einstein mathematically proved the existence of atoms and molecules in 1905 that the matter was truly settled. And you thought Einstein was all about relativity and E equals mc squared. He also proved atoms exist. Here's how it happened. In 1827, a botanist named Robert Brown was looking at pollen grains in water through a microscope, and he noticed that they jiggled randomly even when there was no movement to cause the jiggling. It was a mystery for a long time, until 1905, when Einstein theorized that this phenomenon was caused by as yet unproven atomic particles actually smacking into the grains of pollen. He wrote up some fancy math, showing that his theory predicted this motion almost perfectly, and everyone had to concede that yes, tiny discrete bits of matter were indeed smacking into the pollen, and thus molecules, and by extension atoms, must exist. Today, we remember this botanist and his discovery by calling the motion he observed Brownian motion. It's kind of crazy that every physical thing you've ever interacted with is made up of little ball thingies. It started with people wondering what would happen if you just kept slicing something in half forever. Eventually, and of course it turns out that there's no knife sharp enough to do this, you end up with one pure unbreakable bit of that substance. The word atom, indeed, is from the Greek for indivisible, though, of course, as we learned in World War II, atoms can be broken as well. So, how do you picture an atom in your mind? Like this, or like this, or maybe one of these? If you understand enough about atoms to visualize any of those things, then you know more about atomic theory than scientists did just 100 years ago. And like way more than they thought they knew 2,500 years ago. That's when Greek philosopher Leucippus and his pupil Democritus first came up with the idea that matter is composed of tiny particles. No one knows how they developed this concept, but they didn't think the particles were particularly special. They just thought that if you cut something in half enough times, eventually you'll reach a particle that can't be cut anymore. They gave these particles the name atomos, which means uncuttable or indivisible. So basically they thought that iron was made up of iron particles, and clay was made up of clay particles, and cheese was made up of cheese particles. And they attributed properties of each substance to the forms of the atoms. So they thought that iron atoms were hard and stuck together with hooks. Clay atoms were softer and attached by ball and socket joints that made them flexible, and cheese atoms were squishy and delicious. Now this makes a certain amount of sense if you don't happen to have access to electron microscopes or cathode ray tubes or the work of generations of previous scientists. Because the fact is, atomic theory as we know it today is the product of hundreds, if not thousands, of different insights. Some models, like that of Leucippus, were just blind guesses. As time went on, many more were the result of rigorous experimentation. But, as has been the case in all science, each scientist built on what had been learned before.
Okay, so what is the continuous theory of matter? You have a chair there. See the chair? Okay. Group of Greek philosophers back 2,200 years ago, around 200 years BC, several centuries before the time of Christ, came up with this idea. Their names were Socrates, Plato, and Aristotle, which I can't stand. Chemistry, people just don't like them. I'll explain to you why. This is their theory. You had a chair, cut it in half, you had two pieces of chair. In half, chair. In half, chair. Half, 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 half. We could continue on all period, and you would always have chair. Okay? A chair is made up of an infinite number of smaller chair pieces. Okay? This is the guy. Can't stand him. Aristotle. Socrates. Ugly people. Okay? At the same time, in Turkey, there were other Greek philosophers because, believe it or not, there were Greeks living in Turkey as well. Okay? And they were had a different idea. Their names were Democritus and Leucippus. All right? And they believed that if you had that chair and you cut it in half, you would get chair. And half, 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 half. No! Atoms! You could only go so far, and then you would reach these tiny little indivisible balls called atoms. Okay? Actually, they called them indivisible things, which in Greek is atoms, which the next time you're pledging allegiance to the flag of the United States of America and to the republic for which it stands, one nation under God, atoms with liberty and justice for all.
Whoa.
That's what atoms means. Atom means indivisible. Atom means indivisible. Okay? So, the problem is social media, Facebook, Twitter, Instagram, they all love Socrates. All of them. They all love Aristotle and Socrates. The mainstream media, CNN, CBS, ABC, NBC, they all love Aristotle. Okay? There was one little network, Fox News, that said, no, wait a second, Aristotle is full of it. Democritus is right. There are atoms. The rest of the media labeled them as fake news. So, 200 years before the time of Christ, they had come up with the idea of atoms. It was labeled fake news. So what happened for almost 1800 years? No, 2,000 years, almost 2,000 years. Nothing happened to chemistry. Chemistry was messed up. Chemistry was developmentally delayed is what they used to, you know what that means. Okay, biology was doing great. Physics was doing great. Chemistry, well, that's developmentally delayed. In the 1700s, chemistry was a little better than sorcery, alchemy. I mean, it was just a bunch of people trying to do stuff, and there was no rhyme or reason. It was a great wild west. No laws, no rules, nothing made sense. All because of Democritus and Leucippus being labeled as fake news. All right. Now, if you're interested in what people in the time of Christ said, well, this is the writer of Hebrews. We don't know who it was, but several times in the book of Hebrews, Greek philosophers are quoted. Okay, so whoever wrote the book of Hebrews in the New Testament knew Greek philosophy. And what's really interesting is this last part here comes almost directly from Democritus. Through faith, we understand that the worlds were framed by the word of God, so that things which are seen were made by things which do not appear. So, perhaps that the writer of Hebrews believed in the atom theory, but it doesn't matter. Fake news, everything's screwed up. It wasn't until the 18th century that things started rolling. Okay? What 3 laws led to the development of the atomic theory? The law of conservation of mass, the law of definite proportion, and the law of multiple proportion. Number 4. Oh, it's already there. Great. So what is the law of conservation of matter again? Or matter cannot be created or destroyed, it just changes form. Matter cannot be created or destroyed, it just changes form. That was big, gang. What Antonio Lavoisier came up with was big, because now, for the first time in chemistry history, it was predictable. There was something that was predictable. However much matter you begin with, you better end up with. Nothing's ever lost. Nothing is created. That led to another huge development, the law of definite proportion. And this is what they said. Proportion by mass of elements in a given compound is always the same. The proportion by mass of the elements in a given compound is always the same. No, what that means is, for example, water is made up of hydrogen and oxygen. Wherever Joseph Proust, the guy who developed this law, wherever Joseph Proust went, he found that water was 8 times more oxygen than hydrogen in terms of mass. Most of the mass of water was coming from oxygen. And it's more than that, it was always 8 times more, Elaine. There was a pattern to this. It was a predictable pattern. Anywhere he went, he found that water consisted by mass of the same things, hydrogen and oxygen, by mass, the same proportion. Yes, that was it. Yes, every sample of water. Yes, that was big because that got us a little closer. See, up in this point, this whole idea of atoms was fake news. But so far, the law of conservation of mass and the law of definite proportion seem to be pointing back to atoms. Along came another great Cuban scientist. His name was Juan Daltano, and he came up with this. Whenever elements combine to form compounds, they always did so in small whole number ratios. Small whole number ratios. That was huge as well. Why? Because when you came down to it, water was always 2 parts hydrogen, 1 part oxygen. So guess what he ended up calling parts? Atoms. Atoms. Whenever elements combined together, they always did so in small whole number ratios. He had found evidence for atoms. For atoms. So hydrogen is always 2 hydrogen to, water is always 2 hydrogen to 1 oxygen. Sodium chloride is always 1 sodium to 1 chlorine. He had discovered the evidence for atoms. And then he came up with the atomic theory. Is this already done? The 4 parts of the atomic theory? Okay. So we finally come up to the first model of the atom. Are you ready? No, it's not. What are you talking about? Here it is. This is called the solid sphere model. You ready? According to Dalton, in 1803, this is what an atom looks like. Pencil drop, microphone drop, dab. That wasn't cool anymore? No, okay. No more dabbing. Okay. My son still dabs, I'm sorry. First model of the atom was proposed by Juan Daltano. Tiny little spheres that cannot be broken down any further. It was proposed by John Dalton and the Turkish Greeks. I know, it should be a band. John Dalton and the Turkish Greeks. Yeah, because you'll see that in the worksheets. Turkish Greeks. It wasn't the Greek Greeks. The Greek Greeks gave us what really ended up being fake news. To their defense, yeah, they were wrong about the atom, but they were right about a lot. Most of our culture is based on the writings of Plato and Aristotle. Okay, and even Christianity was influenced greatly by Plato and Aristotle. So even though we in chemistry don't like them, the fact is they did contribute a lot to Western culture. All right, I want to stop right there. All right, so we started out with the Dalton model, which we call the solid sphere model, because it looked like a solid sphere. And then we moved through most of the 1800s, everyone believing that the atom was made up of teeny tiny little balls. Now, near the end of the 1800s, they started playing around with all sorts of different gadgets and toys that made them feel a little uneasy about this whole idea that the atom was indivisible. This is an electroscope, and this is one of the toys they used to play with. Watch what happens.
Okay, I'm going to take this piece of PVC and rub it with this piece of silk so as to transfer electrons from the silk to the PVC. And now we'll see as I bring it towards the electroscope, long before I'm getting close to the plate on the top, you can see a bending of the gold leaf. And this is due to an induced charge on that gold.
Okay, we saw this yesterday when I showed you the FET, right? The little simulation, where we know that we can rub things on different things and it picks up a negative charge. Okay, in this case, they were rubbing that rod on the piece of silk and it was picking up, he called it electrons. Of course, back 150 years ago, they didn't know anything about electrons. They just knew it as negative particles. It was picking up negative particles. The closer he got to this little piece of metal, the further apart these two gold leaves got from each other. Why? Because this stuff was made up of negative particles as well. So when a very negative rod came close to a neutral this, then the negative particles would just stream away from it, get into the two leaves. And of course, these two leaves were so close together that when both leaves became negative, they didn't want to be with each other anymore. So they got away from each other. All right. This was called an electroscope. And we started thinking, okay, so could it be possible that atoms are made up of themselves, smaller things like negative particles? Along came this guy, William Crookes. Notice his awesome mustache. You wish you could grow a mustache where you could take some wax and do the tips like that. I can't. My son does that, but I can't do that. He created this device called the Crookes tube. Basically, he pumped out all the air, attached it to an electric source, and lo and behold, light appeared.
Was why? Why do they behave the way they do? This led to the investigation of atomic structure. In the 1870s, scientists began probing what stuff was made of using discharge tubes, basically gas-filled tubes with electrodes at each end, which emit light when an electrical current passes through them. It's basically what a neon light is. Because this light was originally produced by a negative electrode, or a cathode, it was called a cathode ray, and it had a negative charge. But in 1886, German physicist Eugen Goldstein found that the tubes also emitted light from the positive electrode, basically a ray heading in the opposite direction, which meant that there must also be a positive charge in matter. Goldstein didn't fully understand what he'd discovered here. I mean, scientists still hadn't figured out what was responsible for the negative charge in the rays either. Then, English physicist J.J. Thompson took the discharge tube research further. By measuring how much heat the cathode rays generated, how much they could be bent by magnets and other things, he was able to estimate the mass of the rays, and the mass was about 1,000 times lighter than hydrogen, the smallest bit of matter known at the time. He concluded that the cathode rays weren't rays or waves at all, but were in fact very light, very small, negatively charged particles. He called them corpuscles. We call them electrons. So even though we didn't understand what shapes they took, we knew that there were both negative and positive components to matter. The next question was, how were they arranged in the atom? Thompson knew that the atom overall had a neutral charge, so he imagined that the negatively charged electrons must be distributed randomly in a positively charged matrix. And the very English Thompson visualized this model as a familiar English dessert: plum pudding, the positive matrix being the cake, and the electrons the random floating bits of fruit within it. Even today, Thompson's model of the atom continues to be called the plum pudding model. And while a single electron's motion is random, the overall distribution of them is not. The next...
Okay, so here's J.J. Thompson. And let me show you this Crookes tube that he played around with, or the cathode ray tube. First of all, this is just an interesting machine called an induction coil, which created this stream of negative particles that you see there. I have no idea what would happen if you were to put your finger there. Probably get a nice little shock. All right, now this is a Crookes tube or a vacuum tube. Notice that when you plug it into the negative part of the electricity comes out and streams from one side to the other, creating this beautiful green glow. And everyone would just admire it and go, wow, that's a beautiful green glow. What J.J. Thompson theorized was that that green glow was actually made up of particles, so he brought a magnet close to it. This is the positive side of a magnet. Ruh-roh. See, if this was just pure light, you can't bend pure light. You can't bend it. Not with a magnetic field, anyway. This was crazy. Not only that, but it was bending toward the positive side. Folks, only bending can occur if you are made up of matter, because it's one of the attributes of matter called inertia. All right? So the bending occurred because whatever this was made up of matter and negatively charged. Watch what happened when he brought the other side of the magnet close to it. Can you guess? Yeah, the negative side would repel it. Now, around this time, they started also playing with attaching different things to this vacuum tube to see what would happen. In this case, it's hard for you to see because of this reflection, but can you see a white cross here? That was made of a metal. Watch what happens when you hit it with the cathode rays. You can see it better at dark. So the metal absorbed the cathode rays, but it did more than absorb it, because another scientist working at this time with this kind of tube with metals in it discovered that a strange radiation was being emitted at a right angle from it. In other words, right here where the metal hits, radiation was being emitted in this direction. That's why there's a Geiger tube right there. Radiation was being emitted in this direction from it. Okay, it was a strange radiation. They had never experienced anything like it. They called it radiation X, for the unknown radiation. One of the things he discovered is, I don't know why he had photographic film nearby, but apparently he did. And he had a piece of paper on top. It didn't matter. That photographic film was developed by radiation X, as if it was light, visible light. And those of you who here's in photography, anyone? No? Okay, you know visible light can develop film. This was very strange, so he got all sorts of interesting ideas. His name was W.K. Rengen, and he thought, well, maybe if it can penetrate through pieces of paper, it'll penetrate through skin, and we can see what's inside the human body, get pictures of the insides. So, being a really, really cool German dude, he goes, Hey, wife, get over here. Come here and stand right there. He started taking X-ray pictures of his wife. Why X-ray? Because it was radiation X. Yes, W.K. Rengen had discovered or invented the X-ray machine. Now, so sad, his wife died a few months later. Very strange causes. No one at the time could figure out what killed her. People reading the journals and reading about her symptoms realized after he died, that old cuss killed his wife. Yes. It was, wasn't it? That's ironic. Never heard of that. Okay. Yeah, there's a famous picture where you can see her hand and just you can see her wedding ring and everything. And that plus a few more of those pictures was probably enough to kill her. It's because he was giving her a ton more radiation than they would ever give you at the medical office. Okay. So, yes, put a piece of metal in this tube, and now you have an X ray machine. Yes, very primitive. Okay, when you were little kids, did you ever find this toy? I mean, yeah, it wasn't your iPad and you actually had to move it. I know it's probably something you did not do, right, Maddie? But it was kind of like a yo-yo where you had this metal frame and you had this wheel that was attached to two spokes. And the spokes were magnets and they attached to the metal frame. And if you hit this at a certain rhythm, then this little wheel would spin and place and go back and forth. Well, watch what happens when you put one of those little yo-yos in the spokes here, and you and the instead of it being just a wheel, it has like a little fan blade of metal. Watch. All right, folks, now come on. If there's no air in there, how in the world is it spinning? Unless, of course, the particles were hitting it, making it spin. So, big news. We've got to change our atomic theory. By the way, that tube eventually was placed in the back of a box with a phosphorescent front to it. And as the cathode rays would hit the phosphorescent front, it would glow teeny tiny little bits of light. And at first, it would either glow, it would glow different shades of gray. Eventually, they figured out a way for it to glow red, green, and blue. Okay, really, really big. Back in 1966, they started using these boxes where the phosphorescent screen would glow red, green, and blue. What am I talking about? Televisions. Okay, televisions all had these tubes in the back. Okay, now they were coated with a material that absorbed the X-rays. So your grandma who says, you're getting too close to that screen, you're going to get cancer. Well, yes, if the cathode ray tube had not been coated with that screen, you would be exposing yourself to radiation at different angles, at different angles. But the plasma TVs we have now are completely safe, or we hope they are, and they do not use a cathode ray tube. Does anyone still have one of the old-fashioned televisions at home? Okay, those have a cathode ray at home, in the back. That's why they weigh like a mother. All right, Thompson used the words for negative particles, which was coined by Michael Faraday. He used the word electrons, and it was up to the work of an American scientist, Robert Millikan, to actually tell us how negative it was. This is perhaps the coolest experiment of all time.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays.
Okay, so you got these teeny tiny little drops coming down through hole, in this chamber. As the X-rays are hitting it, it's stripping it of its electrons. And now it's a positively charged oil drop because it's lost its negatives. Okay, so now you have positive oil drops. He starts supercharging these plates so that one plate is super negative and the other plate is super positive. And at a certain point, guess what started happening?
Which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise.
He suspended gravity. Using electricity, he was able to suspend gravity.
Depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th Coulomb.
He came up with experimental values that proved the electrons existed. Okay, so who described the Plum pudding model in 1904 and who proposed it? It was a solid sphere of positive goo with negative electrons embedded in it, J.J. Thompson. All right, let's draw it. So before we draw it, let's go back. What was the first model called? The solid sphere model, and who came up with it? John Dalton and his group, the Turkish Greeks. Now, here is model number 2, plum pudding model. It doesn't remind me of plum pudding since I've never had plum pudding, but apparently plum pudding, I've seen it. It's like a roundish cake with things attached to it, these little pieces of fruit. It's more like fruit cake than it is pudding. What I like to think of is one of my favorite desserts, banana pudding. Ooh. So it's a positive yellow goo with little vanilla wafers and banana slices. Who's ever had banana pudding? Oh man, it's good, isn't it? Now, what? Oh yes, homemade, but not the first day homemade. The second day. Have you ever had it the second day? Yeah, they're mushy and they're kind of blended in. Oh, but if you go too long, then it gets kind of blackish and it's like, no. All right. So we have a second model now of this positive goo with electrons embedded in it. All right. Now, Thompson becomes famous. And when scientists become famous, people from all over the world come to learn under him, learn under you. Okay. A New Zealander by the name of Ernest Rutherford, who had worked with Marie Curie, decided to use what he had learned in order to prove that Thompson was right. This is Rutherford, okay, next to his student, W.H. Geiger. Now, he was famous. The journals write about him. At night, he would go up to his laboratory, especially during storms. You could hear him up there counting. One beaker, ah, ah, ah. Two beakers, ah, ah, ah. Three beakers, ah, 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 ah. Thus, he became known as The Geiger counter. Get it? Geiger counter? Oh, actually, that was a total lie. No, Sesame Street, the count from Sesame Street has nothing to do with Geiger. It may, I don't know. I've never heard it. But this guy was the guy who did invent the Geiger counter, which was used to determine how radioactive something is. All right, so this is Rutherford with his students. The gold foil experiment was based on what Marie Curie came up with. She played around with radiation, folks. She was brilliant. She was also a Cuban scientist, which we know her as Maria Curie. Her name rhymed. And she lived in Poland. She actually is still considered probably one of the greatest chemists of all time. And that was really big. I mean, you might think I'm being kind of sexist. I'm not. Back then, there really weren't that many female chemists. Okay, but not only was she a female chemist, but she was a fantastic chemist in her own right and is now known as one of the greatest chemists of all time and of one of the few handful of people that actually have an element named after him. Rutherford, by the way, this guy has an element named after him as well. Rutherfordium.
Big step was taken by New Zealander Ernest Rutherford in 1909. He designed an experiment using an extremely thin sheet of gold foil and a screen coated with zinc sulfide. He bombarded the foil with alpha particles, which he didn't really know what they were, just that they were produced by the decay of radium, they were positively charged, and they were really, really small. He expected them to just fly right through the foil with no deflection, and many of them did just that. But as it turned out, some of the particles were deflected at large angles, and sometimes almost straight backward. The only explanation for this was that the entire positive charge in an atom, the charge that would repel an alpha particle, must be concentrated in a very small area, an area that he called the nucleus. Because most of the alpha particles pass right through the atoms undeterred, Rutherford concluded that most of the atom is empty space. And he was correct. Rutherford would later discover that if he bombarded nitrogen with alpha particles, it created a bunch of hydrogen ions. Now, he correctly surmised that these tiny positively charged ions were themselves fundamental particles, protons. Now we're getting close to reality.
So this experiment changed everything.
In 1910, Rutherford...
Okay, so this is the basic parts of the of at least Curie's experiment. She had a lead box, and inside the lead box she put in an element that she had discovered that gave off positive particles called radium. So these positive particles go straight through, and this screen right here would detect them. It would glow green wherever they fell. What he added was this gold foil. This gold foil was a super, super, super thin piece of gold foil that was just a few atoms thick. He was trying to prove his teacher, Thompson, to be correct. If the Plum pudding model is correct, there would be nothing big enough to deflect those positive particles. So all of them should go straight through and appear in the back. Boy,
and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil.
Wait a second. What the heck is that one doing there? Okay, yeah, they should all be there. They should not be anywhere around the screen. They should all be there. This was huge. Okay, they were not expecting this.
Oil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Okay, this was really, really big. This proved that there was something massive inside the atom. Okay? This proved the existence of The existence of the nucleus. The nucleus. Okay? Completely unexpected. We now have a nucleus. Nucleus containing positive particles surrounded by negative electrons. And the gold foil experiment led to this. So you need to associate the gold foil experiment with this model. Okay, so let's review. What do we call this one? 1803. No. Solid sphere model. And who came up with it? And the Turkish Greeks. Then came this one in 1897, I think. 1904? The Plum pudding model, by whom? Okay, now we have the nuclear model by Rutherford, but also associates something very important with it, and that experiment is called? Okay, so if you're wondering why they called it that element Rutherfordium, this guy was brilliant. Okay, he first started out studying radioactivity with Marie Curie. He discovered that he enjoyed the atomic structure better. He influenced 10 future Nobel Prize winners. So even though he never received the Nobel Prize, 10 of his students received the Nobel Prize. All right, a few years later, experiments were conducted indicating that Rutherford was wrong. Let's go back to that one. What's wrong with this? This should make perfect sense to you, especially after studying electrostatics. What's wrong with this? Well, yes, the nucleus is positive. What's wrong with it? Yes, Robert. Wouldn't they just crash into the nucleus? Yes, they would just crash into the nucleus. Okay, this was obviously wrong. So we'll pick up here on Monday and finish it up. So, all right, so let's review. So the first model began 2,200 years ago. It was called what? Solid sphere model. Okay, in the solid sphere, everyone thought of the atoms as being like tiny little balls. Solid sphere model. Of course, these people that came up with it, Leucippus and Democritus, we call them the backup group, the Turkish Greeks, right? The Turkish Greeks, because they were Greek, but they lived in Turkey. And their problem was that nobody really liked them. Everyone liked Socrates and Aristotle and Plato, and nobody really liked Leucippus and Democritus, so no one paid any attention. So this idea of everything being made up of teeny tiny little atoms, which they called atomos because they were indivisible with liberty and justice for all, no one paid any attention until another great Cuban scientist by the name of John Dalton came around, and he actually was able to mathematically at least point to the possibility that atoms did exist. And he explored this and came up with ideas that are very similar to what we believe today. But it took about 100 years, but we started realizing that, no, there are things, these atoms can't be called atoms anymore because they're definitely things smaller than an atom. And at least one of those things are these tiny little negative particles that you can brush off of people and things and carpets and zap your cat with. Okay, so along came which scientist? J.J. Thompson, and he came up with the Plum pudding model that had a bunch of negative electrons embedded in a positive goo. JJ had a student by the name of Ernest Rutherford, and he was trying to prove that Thompson was correct, and he ended up proving he was wrong. Not only that, but he ended up discovering the existence of the nucleus. So now we don't no longer have this field of positivity. Now we have a very positive nucleus. Okay, a nucleus, and outside, sitting outside, just kind of twiddling their little electron thumbs were the electrons. Now, this is not going to last very long. Oops, sorry. Oh, went the wrong way. We need to associate with this which experiment? And what is this model called? Okay, we had some serious problems with the nuclear model. Did we talk about this at all on Friday? Okay, what was the problem with the nuclear model? Yes, Robert. What's to stop the negative electrons from crashing into the nucleus, which was positive? Nothing. Okay, so there was something definitely wrong here. So, finally, we needed a Great Dane to come to the rescue. No, not a dog. Not a dog. It was like a guy from Daneland. A Danish. I know it's Denmark. For those of you on the internet, I know it's Denmark. I'm just making fun of it. So this guy from Daneland, let's see. We got through all this, right? Blah, 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 blah. New Zealander, Marie Curie. Aha. Okay. The Bohr model.
These chemists had a fairly good idea of the structure of the atom, they just needed to figure out what exactly the electrons were doing. Enter Niels Bohr. In 1911, the same year the results of Rutherford's gold foil experiment were published, Bohr traveled to England to study with Rutherford. And as a physicist, he was also interested in the mathematical model set forth by German physicists Max Planck and Albert Einstein to explain the behavior of electromagnetic energy. Over time, Bohr came to realize that these mathematical principles could be applied to Rutherford's atomic model. His analysis of the gold foil experiment, calculations based on the proportion of alpha particles that went straight through, those that were slightly deflected, and those that bounced almost completely backward, allowed him to predict the most likely positions of electrons within the atom. Bohr's resulting model, sometimes called the planetary model, is still familiar to most people, probably including you. It represents the electrons in orbits around a small central nucleus. Each orbit can have a specific number of electrons, which correlates to the energy levels and orbitals in the modern model of an atom. And while it's definitely flawed, Bohr's model is very close to reality in some important ways.
All right, so here was the Great Dane. Danish physicist Niels Bohr, 1913, solved this problem by adding to the Rutherford model. All right, so this was number 12. The planetary model was developed by Niels Bohr. Electrons traveling in orbits around the nucleus. Let me help you understand this with a metaphor. Okay, Maddie. You don't know a lot about this. Maddie's family is just a typical middle class family, but her uncle is filthy rich. Uncle, what's his name again? Uncle Randy. So, on Friday, Uncle Randy's going to pick Maddie up from school and look at her and say, you know, you are my favorite niece. Just because you are who you are, I want to give you $100. So he gives you $100, but he looks at you and says, Maddie, I want you to spend this money tonight. I don't want you to save it. I don't want your parents to know about it. Just find a friend, go as far as $100 will take you, and go spend it and have fun tonight. I don't want to see one penny of it tomorrow. Are you okay with that, Maddie? Can you drive? Oh, do you want to get somebody or just want to go alone? Okay, so who are you going to get? Okay, what's his or her name? Sarai. Okay, so I know Sarai. All right, so Sarai. So, or maybe it's a different Sarai. I don't know. You and Sarai, you pick her up and you're off to where? Let's see, $100, Turkey Creek. Yeah, if he had given you $1,000, maybe Atlanta, maybe Nashville, but with $100, Turkey Creek. Okay, so on your way to Turkey Creek, you realize, oh, I better put some gas in the car. So you stop at Solway, get some gas in the car, $20 because you don't want to blow it all on gas. So you still have $80. So by the time you get to Turkey Creek, it's on Friday evening. It's kind of dinner time. So where would you like to eat with Sarai? Oh, Charlie's on Turkey Creek. Oh, very nice. That's probably a $25 meal there, unless you get really fancy. So 25 plus 20 is $45. You still have $65. Where are you going to go now? How about American Eagle, Old Navy? American Eagle. Okay, go to American Eagle. There you find some pants that they bought at Goodwill. They dragged behind a car for a couple of miles. They washed it and then they cut it up into, big fat holes in it. And it's on sale for $45. These used jeans that were dragged behind a truck for 2 miles and then cut up. And yes, they know that teenagers are dumb enough to buy it for $45. Okay, so you buy some nice cut-up jeans for faded, which is what, American Eagle code word for, yeah, we dragged it behind a truck for 2 miles. Faded jeans. So you bought that $45, you have $20 left. Yes, Menchie's. Yes. Menchie's has only come since I became lactose intolerant, but I like to go up to the window and look inside and people getting their ice cream and loading it up with all the toppings. And yeah, that creeper's over there looking at my ice cream. He must be lactose intolerant. Yeah, how sad it is. So, okay, so there are 3 words. You $20. Okay, let's say you have $10. No. Yeah, go back and get some more gas. All right. Now, there are 3 phrases that you need to be familiar with in order to understand the Bohr model. Number 1 is excited state. When he gave you $100, how did you feel? Yes. So were you depressed or excited? Excited. Okay. When you went home, when you had to go home because you realized you were poor, how did you feel? Not as excited. And you had to go home because you realize you're poor and the only place you can really sleep comfortably is at home. But when you do, you don't have to be like where your parents are, right? That's totally uncool. I mean, those people listen to 90s music, and that is like really silly. You like 21st century music like Justin Bieber and Four Corners and all those things. Okay, so you decide you may be stuck at home, but by golly, you don't have to be in the same room with them, right? So you go up to your room. You're not even close to your parents, all right? But nevertheless, because you are poor again, you are effectively grounded. Grounder. Okay? So, according to Bohr, electrons are a little bit like Maddie. Every once in a while, they will gain energy, not money, energy, and go into excited state. When they go to excited state, they get as far away from the nucleus as they possibly can. Okay? It is possible to get so much money. What if your uncle said $100,000? You're moving out, aren't you? Yeah, you're moving out. It is possible to receive so much energy that the electron takes off and never returns to that atom. Okay? But when you gain enough energy, you will go as far away from your parents, the crib, the nucleus, as you can possibly go. But that is not a permanent state, is it? As you start spending money, you start getting a little more and more depressed as you realize it's a coming. There's going to come a point where I will lose it all and I'll have to go back and be ground state is the next phrase. Ground state is as close to the nucleus as you can be. That is where you have enough energy to get away from your parents, but you don't have enough energy to get away from your house. Okay? So, let's see. These, I believe, in your notes, there should just be key words that are missing. Let's see if we can't see Maddie in this. And by the way, the money is called photons. Photons of energy. Photons of energy. So each electron has a minimum amount of energy that it will keep in its lowest orbit and not allow it to crash into the nucleus. This is Maddie's natural state. She is naturally grounded because she is poor. Ground state. Ground state. All right. When an electron gains energy, it will move to a higher orbit or energy level. This higher orbit is called excited state. Excited state. The move will always be temporary and the electron will quickly lose the energy and go back to its lowest orbit or ground state. Ground state. Did we get all those key words? What are we missing? What? Each electron has a minimum amount of energy that will keep it in its lowest orbit and not allow it to crash into the nucleus. That is ground state. We got that one? Okay, when an electron gains energy, it will move to a higher orbit or energy level. This higher orbit is called excited state. This move will always be temporary and the electron will quickly lose the energy and go back to its lowest orbit, which is ground state. Okay, the energy that is absorbed and released is called the photon. Photon, P-H-O-T-O-N, photon. The energy absorbed or released is called a photon and has many of the same characteristics as waves. The higher the orbit, the more energy the electron contains. The closer the electron is to the nucleus, the less energy it will have. The model led to the planetary model that you are now familiar with. What does the planetary model look like? Did we all get these keywords? We got them? All right. Are you familiar with this atomic model? That is not the modern one. We've forsaken this one, but it's the one that we can picture the easiest. So the Bohr model or the planetary model, that's what I'm going to call it, the planetary model. The planetary model is the one that you were probably taught in middle school, even though it's been rejected for about 100 years now. But it is the one that kind of we can picture. We can kind of picture this one. We can't picture the modern one. We cannot picture the modern one. Okay, were you able to draw it correctly? Good? Yes, we're good? It looks like your typical model of the atom, which of course we know is wrong. 1930s and 40s experiments provided additional information, which once again led us to believe that the planetary model was wrong. Describe the modern charge cloud. A truly mathematical model pinpointing the probable location of the electrons in an atom. Most of the electrons are said to be close to the nucleus, with less and less farther away. We no longer think of them as orbiting. They're just moving outside. They just move outside of the nucleus. We got it?
But like everyone I've mentioned in the past couple of minutes, Bohr was at once fantastically right and way off. The problem was those pesky electrons. It was the German theoretical physicist Werner Heisenberg who got everyone to understand just how huge and mind-blowing this electron problem was. But he was also the one who helped tie the whole mess up into a neat little bundle. Using his wicked math chops, Heisenberg discovered that it is impossible to know with certainty both the momentum of an electron, or any subatomic particle, and its exact position. And the more you know about one of those two variables, the harder it gets to measure the other one. So if you can't measure the position or momentum of an electron, you obviously can't say with certainty that the electrons in an atom are all neatly aligned in circular orbits. So he and a new wave of physicists and chemists proposed a new theory, a quantum theory, which proposes that electrons weren't particles or waves. Instead, they had properties of both and neither. By this thinking, the arrangement of electrons around a nucleus could only be described in terms of probability. In other words, there are certain regions where an electron is much more likely to be found. We call these regions orbitals. You know, the very same orbitals that you and I have been talking about. The ones that go by the names S and P and D and F and that form sigma and pi bonds. Those are the things that Heisenberg's theory predicts, and that's the modern understanding of atoms. Because it's based on probability, quantum-style atoms are often drawn as clouds with the intensity of color representing not individual electrons, but the probability of finding an electron in any particular position. For this reason, the quantum model is often called the cloud model of the atom. And now you know! All the people I've mentioned and many
Charge cloud model, and that's what it looks like. The charge cloud model. Just imagine a pinpoint in the middle, and then around it, little dots. And the closer you are to that nucleus, the thicker the dots. The further you are, the less likely you're going to encounter those dots. The dots represent where the electrons are probably located, but we're not sure. Those are dots. So make most of the dots close to the nucleus, with them further and further away from the nucleus, and I think you've got the charge cloud model. All right, so we're done.